Okay, well, good afternoon, everyone. It's top of the hour here, so we will go ahead and get started. Wanted to thank Hach for joining us today. My name is Diane Lechner. I'm the VP of Sales for Midland Scientific, and we've got some folks from the Hach team to go over the minimizing for boiler fouling, and very excited to introduce today Denton Slavacek. He actually grew up farming and ranching in the Texas and Oklahoma Panhandle. His undergraduate degree was from Friends University in Wichita, Kansas, and then he received his master's degree from Oklahoma State University. So Denton served on the faculty at Northeastern Junior College for 13 years as an instructor in chemistry and social sciences. And in 1989, he was hired by Clifford Hach, founder, to work with him on product development. So during his 30-year tenure at Hach, Denton has managed the Hach Technical Training Center, customer support, and technical support. Since 2011, Denton has worked directly with customers and Hach sales as an application development manager within the industrial markets. He also works closely with the Hach R&D group in the development of some new analytical technologies. So very excited to have his expertise on board with us. I'm going to go ahead and hand it over to him. Just a quick reminder to everyone, most of you are on mute. We appreciate that for the background noise. We do have the chat box open for any questions. Feel free to put those in there and we'll address them either at that point in the presentation or at the end. So thank you once again for joining us. And Denton, the floor is yours.
Thank you. I'm going to go off video. I'm in a motel actually traveling on business this week and don't know how fast my internet is. So we're going to make sure that I'm not going to stop my video. But anyway, thank you for this opportunity to visit with you today. Again, my name is Denton, and we're going to be talking a little bit about boiler water and specifically looking at hardness and alkalinity more than anything else, and then what are some good solutions for that. As we're moving through the presentation, kind of the agenda, when we're looking at boiler water, one of the concerns is, whether or not you're going to create scaling in your boilers or in your boiler systems. And also on the opposite, making sure you don't have corrosion. So we're going to do that. And we're going to look at really two key drivers in water quality for medium and low pressure boilers specifically, and that's hardness and alkalinity. And kind of segue from that into the Langmuir saturation index and why that can be important. And then what Hach has available through Midland for as far as analytical tools for managing those processes and resources better, and then some wrap up and key takeaways, any questions and answers you might have. A little background on Hach. Hach has been in business for well over 70 years, started by Clifford and Kitty Hach post-World War II, with very simple test kits that allowed anyone that were willing to read instructions and follow instructions to reliably get accurate results in water quality measurement. Since then, the Hach still has a huge line of test kits, but as well as extensive laboratory systems and online systems for analysis and control. And we work with really great distributors like Midland and all that to help supply these products to our customers. So we're talking about boiler water. The idea is scaling. And I show you a picture over on the right, of course, of extreme scale. And I think we've all seen examples of this at times. But anytime you start getting a buildup of scale in a system, you start getting a lot of problems with heat transfer, head losses, things like that. In extreme cases, you get complete failure. But basically, scale is the deposition of inorganic salts on a boiler and heat exchanger surfaces, often like a calcium carbonate or a calcium sulfate type scale can be forming. Sometimes you get silicate-based scales. So the whole idea then is how do you control that? Because you're constantly bringing water into your boiler. It's always going to have a certain amount of dissolved solids to it. And you're heating that water, you're going through the cycles, and you start cycling up the concentration of some of these dissolved solids. And at some point, you start building up scale. And so a lot of boiler management is really trying to reduce the effects of scaling, but also on the other end, making sure you don't have corrosive conditions as well. So corrosion is the deterioration of the boiler and your heat exchanger metal surfaces. And extreme corrosion, as you get into higher pressure systems, can really be a dangerous thing. You get into pipe rupturing and all that. But by and large, corrosion can really start, deteriorating your capital equipment and everything. So the question then is, what is your water quality? What is your water doing? And that, and then how can you tell? Well, basically, you can't really understand your water quality, and you can't monitor or measure it, unless you can't really control it unless you monitor it and you measure it. And be able to do that, how do you do that measurement? What should you measure? Well, one of the biggest things we deal with in water quality, ubiquitous, is hardness and alkalinity. And those terms are somewhat ambiguous because they can mean different things at different times. But basically, from a standpoint of kind of pure chemistry, hardness is the sum of the multivalent cations in solution. So if you looked at the total concentration of multivalent cations, with calcium, magnesium being far the most predominant, those are what are going to contribute to water hardness. Alkalinity is basically the solution's ability, or water solution, to neutralize acids. So in most natural waters that we deal with, by and large, almost a very high percentage of the alkalinity is bicarbonates, but it also can include carbonate and hydroxides. And then when you get into boiler water treatment, often we'll add phosphates like a trisodium phosphate or something like that also to enhance alkalinity. But hardness and alkalinity, along with the TDS impact, total dissolved solids, will impact corrosion and your scaling indices and overall your water quality. So there are two things that are really, really closely watched in a boiler systems. Let's talk about hardness. As I mentioned, traditionally, hardness is the sum of calcium, magnesium in water. It is also the other multivalent cations, but by and large, very, very high percentage in most waters is going to be, calcium, magnesium. And largely, water is high in calcium, magnesium because, when rain comes down from the sky, it's very pure. It hits the soils and it dissolves the calcium and magnesium minerals in the soil, and they're dominant. And they're more soluble than a lot of other things other than sodium chloride. And so you start getting hardness building up in your water. We always express, pretty much in the industry, hardness as calcium carbonate. Even if it's magnesium or calcium, we express the result as milligrams per liter as calcium carbonate. We do that to kind of get an idea of the equivalent hardness relative to the amount of alkalinity, which we also express in results of calcium carbonate. Now, there's two types of hardness. And again, you need to understand why we get to this term here. There's temporary hardness, and this is your hardness that are a result of carbonates and bicarbonates of calcium and magnesium. Permanent is what we call the non-carbonate calcium and magnesium. This would be calcium, magnesium, sulfates, nitrates, and chlorides. Now, this whole concept of temporary and permanent is really based upon an old method and it's still a very viable method of reducing hardness, which we call lime softening. So in the case of lime softening for reduction of hardness, you basically will remove the calcium and magnesium carbonate-based hardness, but it will not remove your non-carbonate like calcium and magnesium sulfates. That would require something like zeolite water softening, or reverse osmosis, demineralization. So the whole idea behind temporary hardness is that can be removed with lime softening. Permanent is those that would require other processes. Levels of hardness really kind of depends on what you're talking about. The old general water hardness scale, and they used to measure, and some places still do, measure hardness as grains per gallon. It takes 7,000 grains to make a pound, basically 17 grains is a gram, or 17 grains per gallon is equivalent to 17 milligrams per liter. But by and large, most cases nowadays, we actually express hardness as parts per million. And there's just this general graph here where, soft versus slightly hard, moderately hard, hard, very hard, then based upon the results you get there. So if you have a water that's measuring 100 parts per million as calcium carbonate, that would be considered moderately hard water. But again, that's kind of depending upon a lot of things, because if you're in a situation where you have a high pressure boiler, a very high pressure boiler, any hardness would be considered too hard for that type of situation. Medium pressure boilers or lower pressure, not so much. So just understand that this water hardness scale is somewhat dependent upon how that water is going to be used. Let's talk about alkalinity. So alkalinity is the capacity of the water to neutralize acids, often referred to as the buffering capacity. And it really has to do largely with the presence of carbonate, bicarbonate, and carbonate, and hydroxide ions. But again, in natural waters, with pHs, in the slightly alkaline to less stage, less than 8, let's say alkalinity, the pH less than 8.5, pretty much all of that alkalinity is going to be at bicarbonate. But as you get into the more alkaline pHs and all that, you can start getting a higher degree of carbonate because the hydrogen from the bicarbonate will dissociate off. And then, of course, at pHs above 8.4 and get the 8.5 and all that, you also can start getting some presence of hydroxides. All of these, though, together are considered to be the total alkalinity. So it's very important then to have alkalinity in your water to counteract corrosion, but at the same point in time, understand that alkalinity along with your hardness can create scale. And so there's a balance going on. So as I mentioned, in natural waters, the primary constituent of alkalinity is bicarbonate. But as the pH increases, the bicarbonate can dissociate to the carbonate. And then at higher pHs, you start getting the presence of the hydroxide ion. Again, all of these will contribute to the total alkalinity. When you get into typical monitoring and control, the value of total alkalinity is typically the most important. And it's a very simple test you run where you actually titrate or add acid till your water reaches a pH of 4.5. And that gives you an idea then what the neutralizing capacity of that water is. So expressions of alkalinity, they're out there. We often look at M alkalinity, which is total. And essentially we take a water sample and we add a normalized acid to that water, usually like sulfuric acid, till the pH reaches at 4.5. And at that point, the amount of titrant can be calculated back to the total alkalinity. How we know when we reach pH 4.5, it can be done with a pH probe in the water to show you the endpoint. There are also color indicators like brome cresyl green, methyl red, that would give you kind of a rose-colored color at the point where you reach 4.5. P alkalinity is the amount of acid it took to reduce the pH to 8.3. And of course, if you use phenolphthalein, the phenolphthalein would go from a pink to clear, and that would be your endpoint. And then your hydroxide free alkalinity, you look at your 2 times your P alkalinity minus your total to help you calculate. So you can actually start, based on your titrations, you can actually start speciating how much of your alkalinity is, total versus the P alkalinity, the hydroxide, and so forth. I mentioned this earlier, and it really depends on your pressures or your boilers, how much hardness and alkalinity you can handle there. So for an example, if you're dealing with a low pressure boiler, very often if your hardness is around 75 parts per million or less, then that's probably going to be fairly tolerable. And the total alkalinity, you can handle alkalinity clear up to 900. Now, if you're a power plant with supercritical pressures, you've got to be essentially 0 in both of those. So again, hardness and alkalinity levels are really dependent, and how you manage are really dependent often on boiler pressure. So you have to understand what is an acceptable range based upon your water usage. High pressure boilers, very little to no alkalinity. Low pressure boilers would have a certain amount of hardness and alkalinity. So what do we do with hardness and alkalinity once we have the numbers? What can we predict? Well, there's long been what's known as the Langmuir saturation index. And the Langmuir saturation index basically gives you an idea of whether or not your water has a tendency to either form scale in the boiler or be relatively balanced or has a tendency to be corrosive. And so the Langmuir saturation index is a combination of different measurements that includes hardness and alkalinity, but as you'll see later, also includes temperature, total dissolved solids measured as conductivity, and pH. But in all these situations, we basically are looking at this reaction that I've got below here. We're looking at whether or not the water is dissolving or whether the water is scaling. And again, if the water is dissolving, then that could be a corrosive environment. If it's scaling, it's obviously going to be a scaling environment. So how do we balance this water for that? And this is where the Langmuir saturation index came in. Now, just as a matter of trivia, long before that, people actually literally took a piece of marble, special marble, and they would weigh it to a very accurate measurement. Then they would evaporate water on it. And they would see whether or not that evaporated water added to the weight or detracted from the weight to help determine whether or not that water was scaling and corrosion. Obviously, it was a pretty inaccurate way to do things. So the Langmuir saturation index became the way that we estimate the tendency of water to dissolve or deposit calcium carbonate on a pipe wall. Now, that doesn't mean we want to have bare metal. And very often in a situation, we would actually like to have a thin layer of calcium carbonate as a protective layer, because that's going to help prevent direct contact of your water to the metal, which in heated situations, as water becomes more hot and under pressure, things like dissolved oxygen and all that can really increase corrosion. So if you can have then a light shell or coating of hardness on that, of hardness scale, that can actually help bring some protection. So very often getting a thin layer of calcium carbonate can be desirable because it becomes a shield. So again, we use the Langmuir saturation index, or the LSI, to indicate the tendency of the water to corrode or scaling to a curve, and try to actually maybe have it slightly to the scaling side to help maybe have a small thin protective shell at the same time, not getting excessive buildup. As I mentioned earlier, you need to have several things that you have to know. That's based upon the effect of pH on the solubility of calcium carbonate. That's what the Langmuir saturation index is all about. And when water is saturated with calcium carbonate, which can occur at a pH value named pH sat S, which is saturated pH, the water and your calcium carbonate, they're at equilibrium, and the scale will neither be deposited or dissolved. So if you look at my information over here on the left, what we do is the LSI is actually the pH of the water minus the saturated pH. So the whole key is, how do we determine what the saturated pH is? But once we have that value, an LSI of 0 means that the water is either scaling or forming, it's balanced. LSI greater than 0, there's going to be a tendency to form scale. And LSI less than 0, there's going to be a tendency to dissolve calcium carbonate. And of course, the water is going to be more corrosive. So if we're looking at values again, if we had 0, that would be a stable water, 0.2 slightly scaling, all the way up to 3, which would be an extreme. If you had a LSI of 3, you've got a very extremely severe scaling water on that. Corrosive, it just kind of works the other way. A -3 would be a very strongly dissolving water and would be subject to corrosion. So what have you got to know analytically? Well, basically, if you look over on the bottom left of my slide, we mentioned that LSI is pH minus pH of S. And all of a sudden, you get into all kinds of calculations down here, where you get into the log functions of TDS, you get into knowing what all these other log functions. It looks like it's fairly difficult, but actually it's not really. There's tables and there's calculations, but Hach also provides a special way of doing this. Anyway, you measure total alkalinity by titration. You measure calcium hardness by titration. You get your temperature. Usually, your pH probe or your TDS conductivity probe is going to give you the temperature, but you measure your temperature. You measure your TDS by using conductivity and then extrapolating your TDS, and then of course your pH from the pH meter. And then based on those particular values, you then calculate the Langmuir saturation index. I mentioned earlier a little bit about permanent and temporary hardness. In that situation, when you're looking at methods for softening water, it's really kind of the target you're looking for. So for an example, I earlier mentioned line softening. There's different types of line softening. For one, there's what's called cold line softening, which is just basically using ambient temperatures. And there's also hot line softening, where you're using excess heat from a plant to actually create more precipitation. Essentially, lime softening is we're adding excess amount of lime to our process, which then precipitates the hardness out of the water. And that can really do a good job on high volumes of water to reduce hardness. And usually this is satisfactory for low and medium pressure boilers, because if you look at cold lime softening, typically, you can get your hardness down to 30 to 50 parts per million. And in medium pressure, low pressure boilers, that's often good enough. But as you need to have more reduction of hardness, you might go with a hot lime softening, which can reduce more. But very often, you may be going with what's called zeolite softening. And this is a type of anion or a type of cation exchange. But basically, it's actually exchanging sodium for calcium in your water. So if you think of zeolite resin, and this is the same thing as a water softener in the home, you have a resin that's been saturated and then drained. The resin is saturated with sodium. And then as your water passes through this, the calcium and magnesium ions are more dominant and more attracted to the resin than sodium. So they will exchange the sodium off, and the sodium then will be removed, and the hardness will be left behind. And now you have a soft water, or what we call zeolite softening. And this is the difference is this will remove your temporary and your permanent, where the precipitation only remove the temporary hardness. And again, low to medium pressure boilers, but very often zeolite softening, you can many times get less than 1 part per million or less hardness in many cases. More and more common now is reverse osmosis. And reverse osmosis, it probably removes up to 98% of your total dissolved solids. When reverse osmosis is working really well, 95 to 98% of your total dissolved solids is removed. So in this case, it would remove your temporary and permanent hardness, but it would also remove the other dissolved solids, whether we're talking silica, sodium, all your other ionic compounds. You're getting a very high removal of all of your total dissolved solids. And this is often used in higher pressure boilers, but also high purity water, but even more important, as a precursor to revert to ion exchange. You would use reverse osmosis to supply ion exchange demineralization, which really purifies your water down to ultra pure levels. So when you're really needing ultra pure, most power plants, they're going to go through this reverse osmosis, and they're going to go through ion exchange demineralization so that their water is near that 18 megohms in purity. So these are the ways of softening. So precipitation lime softening again. A lot of places use that when the water doesn't have to be absolutely devoid of hardness. Handles very high volumes, can be done quickly. It's not as expensive as some things, and for the volume of water you're using, it can usually reduce down to 3 to 50 parts per million. And this is often the way we treat water for cooling water. One of the biggest uses, if not the biggest use of water other than irrigation in the world, is cooling water. And very often this water is too high in hardness, and so very often it may go through a lime softening first. When you need a little bit less water volumes, then the hot lime softening can be done. Again, that's going to give you better purity. That's done also in some cases. We'll add magnesium to help precipitate out silica. In this situation, when you're doing lime softening, you always want to make sure that you have a residual hydroxide, because as long as you got some hydroxide, means that you're still going to be precipitating available hardness. If you have no hydroxide, you're not going to be precipitating. So pH control is very critical at this point. Understanding what your hydroxide levels are, your alkalinity levels are, all become very important in this process. Zeolite softening, again, is water passing through a bed of zeolite material, and we're exchanging the sodium for the hardness. And again, we're removing now calcium and magnesium ions, both temporary and permanent. Again, this is going to be in situations where your volumes of water are not near what they would be needed for cooling water. This is when you need water is usually less than 500 gallons a minute. So very often boiler water, we will actually feed water for boilers with lime softening on that. Hardness can be reduced to less than 2 milligrams per liter. Some cases I've seen zeolite softening remove hardness down to less than 0.5. Now understand that zeolite softening does not reduce your conductivity. In fact, you actually get a little bit of a spike of conductivity because you're replacing calcium magnesium with an equivalent amount of sodium. So you're not reducing really the TDS of the water. You're reducing the sodium and you're reducing the hardness, but you're changing back, giving that back with sodium. What's really important then is understanding when your zeolite resin is exhausted, when there's no longer is any sodium on the resins to exchange, and being able to measure that with a hardness titration and all that to understand if you're all of a sudden you're starting to see hardness come through your zeolite softener, now you know it's time to regenerate that softener. So again, being able to measure and monitor. So solutions. So how do we do all this? What's out there? The first test that Clifford Hach ever released to the water world was a test for hardness. It was a drop count test where every drop of titrant that you added to a sample of water until it turned a color equaled 1 grain per gallon. And that was the original test. And he actually started the company with that, he and his wife, Kitty, and they built from that. And Hach still sells that simple test kit from that time. But there's also many, many more sophisticated ways of doing this. So what are some of the solutions that Hach and Midland offer for the Langmuir saturation index? This is a great little instrument here. This is called the TitraLab AT1000 auto titrator. So what this does is you simply go get your water sample. And for a nice, pretty picture, they've got the solutions all colored and all that. But if you look at the titrator, there's a beaker of water that has, in that situation, it would be your water sample at known volume, and putting this on there and pushing a few buttons, it's going to actually first titrate that water to a pH of 4.5 and get your alkalinity. You know, it will keep track of what the P alkalinity was. It can keep track of the total alkalinity. At the same time, it's going to be initially measuring the pH of that water and the temperature. And then after that, it's going to titrate for the hardness. And so now you've got your alkalinity, hardness, pH, and temperature. You've got 4 of the 5 parameters you need for the Langmuir saturation index. You would also then separately measure the conductivity of the water, put the conductivity in to the AT1000, it would, as TDS, and then it would use all 5 factors and then it would calculate the Langmuir saturation index for you. Makes it very useful. So really all your user is doing is measuring out a known volume of water precise, getting the conductivity on it, and then starting the titration. And then you would get all of these values along with the calculated Langmuir saturation index. So how do we go about measuring pH and conductivity? Well, the AT1000 has a built-in pH meter, but you still are going to need the electrodes. But also in some cases where you may be doing separate titrations and all that, we have what we call the Hach HQ meters. And these meters are built to, 1 meter will measure your conductivity and your pH. And then you use your choice of pH probes based upon the type of sample you have and conductivity. But going back to the AT1000s, the auto titration really makes it simple because you're not dependent upon how well someone can read a burette. The fact that we provide the reagents and all that, they're already calibrated and standardized for you. So you're going to get a lot more accurate, repeatable results, and it can improve lab safety for you and automatically calculate the Langmuir saturation index. I apologize for the background noise. I'm in a motel room and they're actually doing construction right outside my window. So I apologize for the background noise. So let's look at some examples of scaling or corrosion. So in the case of plant operators performing analysis once a day, they might be looking at the alkalinity. They would look at the hardness, both total and calcium, and also additional water parameters. And then they make their processes change. They make their process changes based upon that data. So the monitoring solutions we're talking about here is like the AT1000 titrator, again, measuring hardness, alkalinity, pH, and temperature, and then a separate conductivity measurement for that. And then from that, you get your automatic calculation. Then you can make adjustments on your plant water as you see how you need to adjust your LSI. Is more, you need to adjust the pH, is more alkalinity needed, etc. So some rapid and key takeaways.
Denton, I'm
Yes.
going to interrupt here real quick. We had a question come through that probably makes sense to ask right here. But
Okay.
somebody asked if Hach offers any continuous online hardness analyzers.
Yes, we do. We offer several. If we go back to lime softening, and we talked about, we go back to the zeolite softening. We talked about the need to watch for regenerating your zeolite softener. We have what's called a hardness monitor. And basically that just allows you to know, you actually have trip points. So you say, I want to know when my hardness breaking through is greater than 5 parts per million. And it would actually alarm whenever the water quality became that high. It would actually alarm. It would also trigger a relay to start regeneration process. We also have online process instrumentation that can directly measure alkalinity and hardness, just like you would in the lab. And if you have one of these that does hardness, alkalinity, pH, you can actually then, with some controllers, actually have that calculate the LSI as well. So yes, we have online instrumentation that will do hardness and alkalinity, and even there's some algorithms to actually calculate online what your LSI would be on that. It's a great question. So actually, Hach's, you measure Hach's alkalinity all the way from the simple drop count test kits that we developed 70 years ago to very sophisticated online instrumentation. Are there any other questions? I guess my main point of this whole presentation is this, and it goes back to, you can't control what you can't measure. And being able to get a good water sample and measuring it really lets you know what you're dealing with, and helps you not only to control it and make adjustments, but to really keep track of what's going on and have a better idea of your boiler water management. Are there any questions here?
Another question that I had here is what is the best treatment for corrosive water?
Yeah, as much as anything, it's pH control. So a lot of times corrosive water is really kind of very often condensate, maybe coming back or something along that line. And, pH control could be adding some alkalinity back into the water. It may be as a caustic type treatment, a small amount of caustic treatment. It can be in some cases the addition of some lime and all that. But basically, you're just trying to get some, the water's corrosive because it doesn't have enough alkalinity. And so you're just trying to get that alkalinity back into the water on that. So different kinds of processes would demand different things, but depending upon your boiler, sometimes you don't get into like a sodium hydroxide feed or things like that. It's a good question. Any other questions?
And then are hardness and alkalinity always equal?
That's a great question. A lot of people think it is. And there are many cases. I mean, if we go back to the raindrop, right? And we track that raindrop and it hits the soil and it dissolves calcium carbonate, then your amount of calcium and your amount of carbonate would be equivalent. And there are a lot of waters out there where there's been very little geologic situations where there's calcium sulfates, gypsum and all that, maybe from past volcanoes or that type of igneous activity. And if that water has largely been influenced by calcium carbonate dissolving or magnesium carbonate, then very often the two can be very close together. They're rarely ever equal because there's always going to be maybe some calcium chlorides or calcium sulfates out there. So I have seen waters that they're usually very close, but often most waters, there's usually more hardness than there is alkalinity. Hardness is usually higher because there would be also not just the temporary alkalinity, the calcium carbonate or, the hardness / alkalinity, but also the more permanent, like calcium sulfates and things like that, also in the water. And when I say calcium, also meaning calcium, magnesium, so forth on that. That's a great question. Often they're close, but as a rule, no, they're usually hardness is higher. And rarely have I ever seen a perfect 50-50 equivalence. Any other questions?
Well, if there are no other questions, I want to thank you again, everyone, for your time today. Thank you, Denton, for your expertise here. For all the folks on the line here, we will get the slides sent out for this and some follow-up information. So please reach out to us for any needs or information that you guys may have. And I hope you have a wonderful rest of your day.
Thank you all.